Imagine standing in the most remote place on Earth, perhaps the Atacama Desert at midnight, or deep in an Antarctic valley where no wind blows. The silence is so complete you can hear your own heartbeat, your blood moving through your veins. That silence, profound as it seems, is cacophony compared to where we're going tonight. Hello, and welcome to the Sleepy Astronomer. If you're settling in for the first time, welcome aboard our contemplative voyage through the cosmos. And if you've travelled with me before to explore distant worlds and cosmic mysteries, it's wonderful to have you back among the stars. Before we begin tonight's journey, if you enjoy these peaceful explorations of the cosmos, I'd be grateful if you'd subscribe to join me for more cosmic journeys. A gentle like helps others discover these late-night wanderings through space and time. Whether you're tucked into bed, curled up in a favourite chair, or perhaps lying back where you can see the night sky through a window, I'm glad you're here for this most expansive of all our journeys. In our last journey together, we followed a single black hole from its violent birth to its gentle dissolution, a story spanning 10 to the power of 69 years. We watched it outlive stars, outlast galaxies, and finally dissolve in a brief, brilliant flash of quantum radiation. The photons from that final burst raced outward at light speed, redshifting as space expanded, dimming with each passing moment. And when the light finally disappeared, stretched beyond any possible detection, the universe entered an era it will spend more time in than all previous eras combined. Tonight, we explore the dark era, the age after black holes, after stars, after even matter itself may have dissolved. This is the universe's longest chapter, an epoch of such profound stillness that entire previous cosmic histories seem like brief introductions. It's a place where time loses meaning because nothing changes, where distance becomes absolute because nothing can cross it, where temperature approaches a limit it can never quite reach. This is the most meditative journey we'll take together. There are no dramatic events here, no explosions or collisions, just the patient work of expansion and cooling, entropy approaching its maximum. The universe settling into a rest so deep it might as well be eternal. If our first episode was a character arc, this one is a tone poem, a contemplation of emptiness, silence, and the strange peace that comes from absolute stillness. So, settle in somewhere deeply comfortable. Maybe darken your room. Close your eyes if that feels right. We're going to explore what it means for a universe to be empty. Not empty in the sense of having nothing, but empty in the sense of having given up all the energy differences that create change, all the gradients that drive transformation. The Japanese have a concept called ma, the space between things. Not empty space, but charged space, pregnant with potential. In traditional Japanese aesthetics, the silence between notes in music matters as much as the notes themselves. The blank space in a painting gives meaning to the brush strokes. These are not absences, but presences. The dark era is cosmic ma, the vast silence that gives meaning to the brief, bright age that preceded it. Without this darkness, the earlier light means nothing. Without this silence, the earlier sound cannot be appreciated. What makes this different from previous cosmic eras is the lack of protagonists. Previous eras had stars being born, galaxies colliding, black holes merging. The dark era has no protagonists, only a stage. The universe itself becomes the focus, not as a container for events, but as a state of being. We're not following a character through this era. We're becoming intimate with emptiness itself. Yet even in this emptiness, physics continues. Dark energy keeps expanding space. Quantum mechanics keeps producing virtual particles that flicker into and out of existence. Perhaps protons decay over 10 to the power of 34 years, turning matter into radiation. The cosmic microwave background continues its patient cooling toward absolute zero. These processes are so slow, so subtle, that they're almost non-processes, changes that take longer than the universe has existed so far to produce measurable effects. There's something both terrifying and comforting about this vision. Terrifying because it represents the end of relevance, a universe where nothing we recognize as important can happen anymore. But comforting because it represents perfect rest, the ultimate peace, a state beyond struggle and loss because there's nothing left to struggle for or lose. The Buddhist concept of shunyata, emptiness, will be our companion through this journey. Not emptiness as mere absence, but emptiness as the fundamental nature of all things, a pregnant void from which everything arises and to which everything returns. The dark era is the universe discovering its own shunyata. The last black hole has evaporated. Its final burst of gamma rays is speeding away at light speed, growing dimmer, redder, longer in wavelength with each passing moment. Within a few thousand years, those photons will have red-shifted into radio waves. Within a few million years, their wavelengths will be measured in light years. Eventually, they'll be stretched so thin that they're indistinguishable from the vacuum itself. Let's watch what remains. Picture the moment after an orchestra's final note fades, that suspended instant where silence hasn't quite settled, but sound has already ceased. The universe is in that moment now. The black hole is gone. Its final burst of energy is propagating outward through space, and in the region where it was, only flat space-time remains. The black hole's final moments released one solar mass worth of energy, the entire mass of our Sun, converted to radiation according to Einstein's equation. The release happened in roughly 1 Planck time, 10 to the power of minus 43 seconds, the shortest meaningful duration in physics. If you could somehow watch from outside, the power would be incomprehensible, approximately 10 to the power of 90 watts, more than all the stars that ever burned combined, though of course there were no stars left to compare it to. In that instant, the universe was flooded with the most energetic light. Physics allows gamma rays so powerful, their wavelengths were smaller than atoms by 20 orders of magnitude. Every kind of particle the laws of physics permit flickered briefly into being. Electrons and positrons, quarks and antiquarks, neutrinos of every flavor. A brief shudder of gravitational waves accompanied the evaporation as the black hole's structure finally gave way to quantum mechanics. The photons from that burst are now expanding outward in all directions at light speed, exactly 300,000 kilometers per second, the cosmic speed limit, but space is expanding too, and as it expands, wavelengths stretch. This is what astronomers call redshift, and it's relentless. As trillions of years pass, those fierce gamma rays unwind into softer and softer colors. First X-rays, visible only to instruments that no longer exist. Then ultraviolet, the light that once gave Earth its sunburns. Then visible light, red, orange, yellow, green, blue, though there are no eyes to see it, no retinas to catch those photons. Then infrared, the warmth humans once felt on their skin. Then microwaves, the radiation that once heated food in boxes on kitchen counters. Then radio waves with wavelengths measured in kilometers, then in light years. Eventually the wavelengths will be measured in distances larger than galaxies once spanned, stretched so thin by cosmic expansion that they're nearly indistinguishable from the fabric of space itself. So what remains in the universe at this point in cosmic history? Let's take inventory slowly, category by category. Let's begin with the light. All of it, ancient and newborn, scattered across the expanding dark. Photons from this black hole evaporation we just witnessed, spreading outward at their constant, patient speed. Ancient photons from earlier black hole evaporations that happened trillions of years ago, now stretched and cooled beyond recognition. The cosmic microwave background, that afterglow of the Big Bang itself, now incredibly cold and stretched to wavelengths of thousands of kilometers. Neutrinos from various decay processes over the eons, ghostly particles that barely interact with anything, passing through each other and through space as if neither existed. And gravitational waves from ancient mergers, ripples in space-time stretched to wavelengths that span distances larger than galaxies once did, carrying memories of collisions that happened when the universe was young. Beyond the fading light, the universe also holds the last traces of matter. Whether any solid matter remains depends on whether protons decayed. If grand unified theories are correct, and protons do decay over timescales of 10 to the power of 34 years, then most matter has dissolved by now. What remains are roughly 10 to the power of 80 electrons scattered throughout what was once the observable universe. There's also an equal number of positrons, their antimatter twins and neutrinos, perhaps 10 to the power of 80 or more. If dark matter particles are stable, and we don't know if they are, they persist too, though we don't know how many or what they are, or what they do, or whether they notice the emptiness around them in whatever strange way dark matter might notice things. And as for anything larger, anything built, the universe has moved beyond such complexity. Galaxies, stars, planets, even stellar remnants, all are gone, either decayed through proton decay or consumed by black holes. All black holes below about 1 million solar masses have evaporated through Hawking radiation. Only supermassive black holes remain, those giants that once anchored galactic centers, and we'll talk about them in a moment. No gravitationally bound systems survive, no orbits, no rotation, no structure. The universe has become profoundly simple, just particles and radiation spread almost uniformly through expanding space. The cosmic census reveals stark numbers. Photons number roughly 10 to the power of 88, a 1 followed by 88 zeros, most of them produced by black hole evaporation over the eons. Neutrinos number about the same as photons. If protons decayed, electrons and positrons each number around 10 to the power of 80. The average density of the universe has fallen to roughly 10 to the power of minus 120 grams per cubic centimetre. To put that in perspective, imagine a cube of space 10,000 kilometres on each side, about the diameter of Earth. On average, that entire volume contains just one particle, and this density continues falling as space expands. The temperature of space tells its own story of cooling. The cosmic microwave background started at about 3000 Kelvin when it was released 380,000 years after the Big Bang, hot enough that the universe glowed like the surface of a red dwarf star. By the time human civilization arose on Earth, it had cooled to 2.7 Kelvin, just barely above absolute zero, but still warm enough to detect with radio telescopes, still leaving a faint hiss in television static. At 100 trillion years into cosmic history, it reached about 1,000th of a Kelvin. At 10 to the power of 19 years, it measured 10 to the power of minus 13 Kelvin. Now, at 10 to the power of 70 years after the Big Bang, it sits at roughly 10 to the power of minus 30 Kelvin. That's 30 orders of magnitude colder than absolute zero, a decimal point followed by 29 zeros and then a 1. And it's still falling, cooling proportional to 1 over time, approaching but never reaching absolute zero, because quantum mechanics forbids perfect stillness. The energy density of the universe has become vanishingly small. At temperatures this low, radiation carries almost no energy. The energy in all the photons filling a cubic meter of space is roughly 10 to the power of minus 130 joules, a number so small it's almost meaningless. For comparison, the quantum vacuum itself, empty space with all its zero-point fluctuations, its virtual particles popping in and out of existence, has an energy density of about 10 to the power of negative 9 joules per cubic meter. The universe's actual radiation is negligible compared to the quantum foam underlying space. Dark energy now utterly dominates. It maintains its constant density of about 10 to the power of minus 9 joules per cubic meter, regardless of how much space expands. This means dark energy makes up more than 99.99999% of everything. Matter and radiation have become trace impurities in a universe made almost entirely of dark energy. This complete dominance of dark energy means the expansion of space continues at a steady, unrelenting rate. The Hubble parameter, the measure of expansion rate, sits at roughly 10 to the power of minus 18 per second. This translates to a doubling time of about 10 billion years. Every 10 billion years or so, all distances in the universe double. This continues forever, or at least as long as dark energy remains constant. There's no deceleration, no mechanism to slow the expansion. No big crunch will ever occur. The expansion is eternal. Following individual particles reveals the profound isolation. Imagine two particles, let's say electrons, released in the same black hole evaporation. Initially, they might be separated by mere kilometers. After 10 to the power of 10 years, they're light years apart. After 10 to the power of 11 years, thousands of light years separate them. After 10 to the power of 12 years, millions of light years. After 10 to the power of 13 years, billions. They will never interact again. They cannot see each other, cannot influence each other, cannot know about each other's existence. Each one exists alone in its expanding bubble of space. The observable universe, that region from which light can reach a given point, is actually shrinking in a certain sense. It's not that space itself is contracting, but that the cosmic event horizon, the boundary beyond which objects recede faster than light can travel, maintains a relatively constant size while everything inside it spreads apart. Currently, this horizon sits at roughly 16 billion light years. Objects beyond this boundary are forever unreachable, forever invisible, forever cut off from causal contact. And as time passes, more and more of the universe crosses this boundary, disappearing beyond the horizon, lost to observation and interaction. The supermassive black holes deserve special attention. They're the only remaining structures, the last organized objects in the cosmos. Roughly 10 to the power of 11 of them exist in what was once our observable universe, one at the center of each former galaxy. Their masses range from about 1 million to 10 billion solar masses. They're separated by average distances of about 100 million light years, though that distance is growing exponentially with time. Their temperatures are incredibly low, between 10 to the power of minus 17 and 10 to the power of minus 19 Kelvin, far colder than the cosmic microwave background was for most of history. But now, for the first time, something remarkable has happened. Space itself has cooled below their temperature. For 10 to the power of 70 years, these black holes absorbed more radiation than they emitted. Now they're warmer than their surroundings. They're radiating more energy than they absorb. They're heating space infinitesimally rather than cooling from it. This reversal marks the beginning of their true evaporation. For eons, Hawking radiation was overwhelmed by absorption from the cosmic microwave background. Now Hawking radiation dominates. A billion solar mass black hole will take roughly 10 to the power of 99 years to evaporate completely. 10 to the power of 99 years, a number so large that our current age of 10 to the power of 70 years seems instantaneous by comparison. These black holes have barely begun their dissolution. They've lost essentially none of their mass. But the clock is ticking quantum mechanically, one particle at a time. We've crossed a threshold, not a dramatic one. There was no explosion, no catastrophic collapse, no sudden transformation. Just a gentle transition from a universe that still had rare events to a universe where essentially nothing happens. This is what endings often look like in reality. Not bang but whimper, not climax but fade. The universe has spent 10 to the power of 70 years reaching this point, and now it will spend far longer here in this state of near-perfect equilibrium, longer than all previous time combined. Tibetan Buddhism describes bardos, intermediate states between death and rebirth. The most famous is the bardo of dying, when consciousness transitions from life to whatever comes next. But there's also the bardo of becoming, a state of pure potential waiting for conditions to arise. The dark era is the universe's bardo of becoming. The previous life, the stellar era, the black hole era, has ended. What comes next, if anything, hasn't begun. In between the two is this vast, quiet waiting. The universe is like an empty concert hall after everyone has left. The orchestra is gone, the audience departed, the lights turned off, the doors locked. Yet the hall remains, empty, silent, waiting. Not waiting for anything particular, just waiting the way empty spaces do. The acoustic space persists without sound. The stage remains without actors. Time continues without events. To understand how empty the universe has become, consider this. The average distance between particles is now millions of light years. If you were a photon travelling at light speed, you might go billions of years without encountering anything. If you were conscious, which is impossible, but imagine, you'd see nothing. Perfect darkness in all directions. No reference points, no landmarks, just the patient expansion of space itself, carrying you and a few scattered particles farther and farther apart. Imagine being an electron released in a black hole evaporation 10 to the power of 60 years ago. You've been travelling through space since then, perhaps given some tiny initial velocity by the quantum randomness of the evaporation. But you've never encountered another particle. No photons have hit you. They're too rare, too spread out. No fields affect you. They're too weak, washed out by expansion. You just drift through expanding void, alone, forever. This is the fate of roughly 10 to the power of 80 electrons scattered throughout the universe. The black hole's final flash has faded into the expanding darkness. The photons it released are red-shifting toward invisibility, their wavelength stretching toward infinity. We've taken inventory of what remains, mostly radiation and particles, spread inconceivably thin across space that continues growing without limit. But we haven't yet grasped the true scale of the emptiness. To understand the dark era, we must comprehend not just that things are far apart, but how far. Distances so vast they make intergalactic space seem crowded. Distance is a relative concept. A mile feels far when you're walking, negligible when you're driving. The distance to the grocery store is measured in minutes. The distance to another city, in hours. We think of the moon as distant, 240,000 miles away, until we remember that light crosses that gap in just over a second. The Sun, 93 million miles distant, seems impossibly far until we learn that its light reaches us in 8 minutes. Even the nearest star, Proxima Centauri, 4 light-years away, feels graspable somehow. We can imagine waiting 4 years. We've done longer things. But the dark era operates on a different scale entirely. Not just larger numbers, but a fundamentally different category of separation. These are distances that redefine what far means. Distances so vast that even travelling at the speed of light, the fastest speed possible, the cosmic speed limit, the velocity at which causality itself propagates, you would spend longer crossing them than the universe has currently existed, and you still wouldn't be close. Let's start with something we can almost grasp, and work our way toward the incomprehensible. Right now, in our era, galaxies are separated by millions of light-years. The Milky Way and Andromeda, our nearest large galactic neighbour, are about 2.5 million light-years apart. That's far, absurdly far by human standards. A photon leaving Andromeda when our Australopithecine ancestors were learning to walk upright is only just now arriving at Earth. The light you see from Andromeda tonight left before humans existed in any form we'd recognise. But galaxies, despite these distances, can still interact. Andromeda and the Milky Way are in fact on a collision course. In about 4 billion years they'll merge, a slow-motion cosmic dance spanning hundreds of millions of years, but a dance nonetheless. Gravity reaches across the void between them. They can still affect each other, still feel each other's presence, still be drawn together. In the dark era, nothing is drawn together. Space itself is expanding, and not just expanding, but accelerating. This is dark energy's doing, that mysterious component that makes up about 70% of the universe's total energy, the thing we've given a name to without really understanding what it is. Dark energy doesn't clump like matter or thin out like radiation. It maintains constant density as space expands, which means as the universe grows, the total amount of dark energy increases. More volume means more dark energy means faster expansion. Means more volume means more dark energy, a feedback loop that never stops. In our current era, this expansion is noticeable but manageable. Distant galaxies recede from us, their light stretched into the red end of the spectrum as the space between us grows. The most distant galaxies we can observe are moving away from us faster than light, not because they're travelling through space at superluminal speeds, which would violate relativity, but because space itself is expanding between us. New space is being created in the gap, carrying them away. But in the early dark era, at around 10 to the power of 70 years after the Big Bang, expansion has been continuing for so long that everything has been carried incomprehensibly far apart. Imagine 2 particles, let's say 2 electrons, released in the same black hole evaporation event. In the moment of their creation, they might be separated by meters, just ordinary, human-scale meters. You could walk the distance between them. In the first billion years after their release, they drift apart to distances measured in light-years still conceivable. We have spacecraft that have travelled for decades through our solar system. We can imagine travelling for millennia or even millions of years to bridge such gaps. After 1 trillion years, they're millions of light-years apart. This is galactic scale separation now. Still, in some abstract sense, we can hold this in our minds. We've seen pictures of galaxies separated by such distances. We know they exist at the scales, but then the numbers begin to escape us. After 10 to the power of 20 years, these 2 particles are separated by distances larger than our current observable universe. The entirety of everything we can see, Every galaxy, every cluster, every filament of cosmic structure stretching 46 billion light-years in every direction would fit in the gap between them with room to spare. And they're still drifting apart. By the time we reach 10 to the power of 70 years, where we are now in the dark era, those two electrons are separated by a distance we might write as 10 to the power of 30 light-years. To put this in any kind of perspective is almost impossible, but let's try. If the observable universe were shrunk down to the size of a single atom, one of those tiny nuclei surrounded by electron clouds that make up everything you can touch, then the distance between these two particles would still be larger than the original observable universe. You'd need to shrink the universe by a factor so large it requires scientific notation to express, and the resulting distance would still be cosmic in scale. Here's another way to think about it. Light travels fast, absurdly fast. It crosses the width of a proton in about 10 to the power of negative 24 seconds. It reaches the moon in just over a second. It spans our solar system in hours. Yet that same light, travelling for 10 to the power of 30 years, a 1 followed by 30 zeros, a million trillion years, would only just barely cross the distance between those two electrons. The universe has currently existed for about 10 to the power of 70 years in our scenario. That means these particles would need to travel at light speed for a duration 1 trillion times longer than the universe's current age to reach each other. They will never meet again. This isn't a practical limitation. It's not that we lack the technology to bring them together, or that it would simply take too long for any civilization to wait. It's that the expansion of space itself makes their reunion impossible, even in principle. The distance between them is growing faster than light can cross it. If one electron emitted a photon directly toward the other, that photon, travelling at the maximum speed allowed by physics, would never close the gap. It would spend eternity chasing a target that recedes faster than it can approach. This is what cosmologists call being beyond the cosmic event horizon. Not a horizon in space, like the edge of a planet or the boundary of a visible region, but a horizon in time and causality. Events beyond this horizon cannot affect you. Light from beyond cannot reach you. No signal, no force, no information can bridge the gap. For all practical and theoretical purposes, regions beyond your cosmic event horizon exist in a different universe. In the dark era, almost everything is beyond almost everything else's cosmic event horizon. The supermassive black holes, the last remaining structures slowly evaporating through Hawking radiation, are each isolated in their own causally disconnected bubble of space-time. The nearest neighbour to any given black hole might be 10 to the power of 40 light-years away. That's 10 to the power of 20 times farther than the particles we discussed earlier. A separation so vast that our previous incomprehensible distance would be like comparing a proton's width to the size of our solar system. These black holes will never see each other. The radiation they emit as they slowly evaporate, those precious few photons released every few trillion years, will travel outward at light speed, but the black holes themselves are receding faster. The photons chase targets they can never catch, travelling forever through expanding space, their wavelength stretching longer and longer as they go, their energy diminishing until they're indistinguishable from the quantum vacuum itself. If you are somehow a conscious observer, impossible in this era, but let's imagine, you would exist in perfect isolation. Not loneliness in the sense of missing companions you once had, because there would be no memory of connection, just existence in absolute solitude. You could observe the space immediately around you, perhaps a few light years in radius, But beyond that, nothing. Not darkness in the sense of a place where light could shine but doesn't. Just nothing. No there to be dark. The universe beyond your horizon doesn't exist for you in any meaningful sense. This is radical isolation, not the poetic loneliness of being far from home, but the ontological impossibility of other. The universe has fragmented into causally disconnected regions, each one its own island universe, each one unable to know about or influence any other. And yet, paradoxically, the universe hasn't gotten smaller. It's gotten larger, vastly larger. The volume of space has increased by factors we'd need towers of exponents to express. But the ability of different parts of that space to interact with each other has decreased to essentially zero. Imagine an ocean so vast that individual water molecules are separated by light years, each molecule still part of the same ocean in principle, occupying the same continuous space, but so dispersed that they might as well be alone in existence. That molecule could drift for the entire age of the universe without encountering another. It could drift for 1 trillion ages, and the probability would barely change. That's the dark era ocean we're swimming in, if swimming is even the right word for this glacial drift through expanding emptiness. There's something almost peaceful about this realization, though. In human life, isolation often comes with the ache of separation, the knowledge that others exist somewhere, that connection is possible but denied to us by circumstance or distance. But in the dark era, there's no ache because there's no expectation. Particles don't yearn for connection. They simply exist, following their trajectories through space-time, obeying the equations of motion, being exactly what they are without any sense of lack. The universe has become a collection of hermits, each one perfectly content in solitude, because contentment and discontent both require something the universe no longer has, the energy to maintain states of wanting. Physics continues, of course. Particles still have mass, charge, momentum. Quantum fields still exist at every point in space, still fluctuating according to the uncertainty principle. The laws of nature haven't changed, but the grand narrative of cosmic evolution, stars forming, galaxies colliding, black holes merging, structures growing and changing, has ended. What remains is just existence. Pure, simple, disconnected existence. In cosmology, there's a concept called the Hubble radius, the distance at which objects recede from you at the speed of light due to cosmic expansion. Beyond the Hubble radius, recession velocities exceed light speed. In our current era, the Hubble radius is about 10 billion light-years. It's large, but it's not infinite. There are things beyond it. In the dark era, your Hubble radius is much smaller, in relative terms, because expansion has had so long to do its work. The sphere of space that you could, even in principle, have causal contact with has shrunk to a tiny fraction of the universe's total volume. And that sphere is shrinking further with each passing moment, not in absolute terms, but in terms of what fraction of the universe it represents. You're becoming less and less connected to the whole, not because you're moving away from it, but because the whole has stretched beyond all possibility of wholeness. And this will continue. In another 10 to the power of 10 years, a mere 10 billion years, the blink of an eye compared to the ages we've been discussing, every distance will have doubled. The electrons that were 10 to the power of 30 light-years apart will be 2 times 10 to the power of 30 light-years apart. The black holes will be twice as isolated. The universe will be twice as fragmented. This doubling will happen again and again, forever, without end, without slowing, without any mechanism to stop it. By 10 to the power of 80 years, distances will have doubled 10 billion times. By 10 to the power of 90 years 100 billion times. The numbers become meaningless, not because they're inaccurate, but because they describe a reality so far removed from anything we can experientially grasp that our intuitions completely fail. And yet, in the midst of this incomprehensible vastness, in the gaps between particles separated by distances that dwarf universes, something persists, the particles themselves. An electron doesn't care that its nearest neighbour is impossibly far away. It simply exists, a tiny knot of charge and mass in the quantum field, following its trajectory through space-time being exactly what it is. There's a kind of dignity in that, existing without purpose, without connection, without witness, but existing nonetheless. The universe doesn't need an audience. It doesn't need meaning. It simply is. And that is enough. We're about to go deeper into that stillness, into the cold that accompanies this vast separation, because distance isn't the only thing approaching an extreme in the dark era. Temperature is falling too, dropping toward a limit it can approach forever without ever quite reaching. But for now, let's rest here in the vastness, these immense distances that make infinity feel personal, that turn the cosmos into a collection of isolated moments scattered across an ocean too large to have shores. The universe is far apart now, and it will only grow farther. Cold is the absence of heat. That's the simple definition, the one that works for everyday life. When winter arrives and you feel the chill, what you're really feeling is the absence of thermal energy. Molecules moving more slowly, transferring less kinetic energy to your skin, creating that sensation we call cold. But cold, like distance, is relative. A winter day might feel frigid at 0 degrees Celsius, but that's tropical compared to the inside of your freezer at -18. Your freezer is balmy compared to liquid nitrogen at -196 degrees Celsius, and liquid nitrogen is practically sweltering compared to the depths of interstellar space, where temperatures hover around 3 degrees above absolute zero. Absolute zero, that's the limit. -273.15 degrees Celsius, 0 Kelvin, the temperature at which, theoretically, all thermal motion stops, not slows down. Stops. Particles cease vibrating. Energy settles into its lowest possible state. The universe achieves perfect stillness. Except it can't. This is one of those beautiful frustrations built into the fabric of reality. Absolute zero is unreachable. Not because we lack sufficiently powerful refrigerators, though we do, but because quantum mechanics simply won't allow it. The closer you get to absolute zero, the harder it becomes to extract the remaining energy. It's like trying to remove the last drop of water from a sponge. The closer you get to completely dry, the more effort it takes to squeeze out what little remains. And with temperature, that final approach requires infinite energy and infinite time. The universe in the dark era doesn't care about our engineering limitations. It has infinite time, and yet even the universe cannot reach absolute zero. The reason has to do with Heisenberg's uncertainty principle, that fundamental quirk of quantum mechanics that says you can't know both a particle's position and momentum with perfect precision. If a particle were perfectly still, momentum exactly zero, then its position would be completely undefined. It could be anywhere. Everywhere, nowhere specific. And that kind of infinite uncertainty requires infinite energy. So particles must always retain some minimum motion. Even at absolute zero, if such a thing could be reached, particles would still jitter and vibrate with what's called zero-point energy. This isn't heat in the conventional sense. It's not thermal motion that you could extract and use to do work. It's just the irreducible quantum restlessness of existence itself. The vacuum isn't empty. Space isn't still. Nothing ever truly rests. In the Dark Era, at around 10 to the power of 70 years after the Big Bang, the universe has been cooling for an incomprehensibly long time. The cosmic microwave background, that afterglow of the Big Bang, the radiation that filled the universe when it first became transparent, has been red-shifting and cooling as space expands. When this radiation was first released, about 380,000 years after the Big Bang, it had a temperature of around 3,000 Kelvin, hot enough to glow orange-red like a heating element on a stove. Over the next 13.8 billion years, as space expanded, that radiation cooled to about 2.7 Kelvin. That's cold. That's colder than anything that exists naturally in our solar system. It's the ambient temperature of empty space between galaxies. But the cooling didn't stop there. It has never stopped. It will never stop. By the time stars stopped forming and the stelliferous era ended, around 100 trillion years after the Big Bang, the cosmic microwave background had cooled to around 1,000th of a Kelvin. By the time the last stellar mass black holes evaporated, around 10 to the power of 70 years, it had cooled to something like 10 to the power of minus 30 Kelvin. That's a decimal point, 29 zeros and then a 1. A number so small it barely qualifies as above zero at all. To put this in perspective, the coldest temperature ever achieved in a laboratory on Earth is around 10 to the power of minus 10 Kelvin. Researchers using laser cooling and magnetic traps have managed to slow atoms to near stillness, creating clouds of ultra-cold matter where quantum effects dominate and classical physics breaks down. It's an extraordinary achievement, the result of decades of work by some of the most brilliant minds in physics. The Dark Era is 10 to the power of 20 times colder than that, 20 orders of magnitude. The difference between a human body temperature and the coldest lab temperature is trivial compared to the difference between that lab temperature and the Dark Era. What does this coldness mean, practically speaking? For one thing, it means that any particles with mass, electrons for instance, if they still exist after proton decay has run its course, are moving extraordinarily slowly. Thermal velocity depends on temperature, and at 10 to the power of minus 30 Kelvin, an electron would be drifting at about 10 to the power of minus 15 meters per second. That's 1 femtometer per second. A femtometer is 10 to the power of minus 15 meters, roughly the size of a proton. So our electron is moving at about 1 proton width per second. For comparison, continents drift faster. The atoms in a solid at room temperature vibrate faster. A snail crossing a sidewalk is a speed demon compared to this electron. Almost perfectly still, but not quite. Never quite. The photons that make up the cosmic microwave background are still travelling at the speed of light. Photons always do, but their wavelengths have been stretched to absurd lengths. A typical photon in the Dark Era has a wavelength measured not in nanometers or even meters, but in light years. Tens of light years, perhaps hundreds. The distance from the Sun to the nearest star is smaller than the wavelength of a single photon. These aren't really photons in any meaningful sense anymore. They're ripples in the electromagnetic field, so stretched out, so low in energy, that they're barely distinguishable from the quantum vacuum fluctuations that permeate all of space. And yet they're warmer than something else in the Dark Era, the supermassive black holes. This is a strange reversal. For most of cosmic history, black holes have been the coldest objects in the universe. A stellar mass black hole, a few times the mass of our Sun, has a temperature of around 10 to the power of minus 8 Kelvin cold. Very cold. Much colder than the cosmic microwave background in our current era. These black holes don't emit much radiation. They absorb more from their surroundings than they emit as Hawking radiation. Their net energy sinks, slowly gaining mass from the universe around them. But supermassive black holes are colder still. A billion solar mass black hole has a temperature of around 10 to the power of minus 17 Kelvin. For most of the universe's history, these have been the coldest objects that exist. Colder than the space around them, colder than the cosmic microwave background, colder than anything. But in the dark era, something has changed. The cosmic microwave background has cooled to 10 to the power of minus 30 Kelvin. The supermassive black holes, meanwhile, are still at 10 to the power of minus 17 Kelvin. They're warming up, not because they're generating heat, but because the universe around them has gotten colder. For the first time in cosmic history, black holes are warmer than their environment. This means they're now radiating more energy than they absorb. The balance has tipped. Instead of slowly accumulating mass from the universe, they're losing it. Their evaporation has begun in earnest. It will take them another 10 to the power of 98 to 10 to the power of 106 years to evaporate completely. Time frames that make the current age of the dark era seem like an eye blink. But the process has started. In a universe approaching perfect coldness, black holes have become heat sources. Tiny, insignificant, nearly negligible heat sources, emitting a photon every trillion years, but heat sources nonetheless. They're the universe's last campfires, burning so slowly that you could watch one for the entire current age of the universe and never see it flicker. But they are burning, and eventually they'll go out. The universe is approaching equilibrium. Not the equilibrium of a system at rest, but thermodynamic equilibrium, a state where temperature is uniform everywhere, where no energy gradients exist to drive change, where entropy has reached its maximum and no further increase is possible. This is what physicists call heat death, though the term is something of a misnomer. The universe isn't dying of heat, it's dying of the lack of heat, or more precisely, the lack of temperature differences. It's not that everything is cold, it's that everything is the same temperature, and when everything is the same temperature, heat cannot flow, energy cannot move, work cannot be done, change cannot happen. The second law of thermodynamics, entropy always increases, has been grinding toward this conclusion since the Big Bang. Every process that has ever occurred, every star that has ever burned, every particle that has ever collided has increased the universe's total entropy. And entropy, in a closed system, can only go up. It approaches a maximum. And when it reaches that maximum, the system is in equilibrium. Nothing can happen anymore, because there's nowhere for energy to flow, no gradient to drive it downhill. We're not quite there yet in the dark era. The supermassive black holes represent a slight deviation from perfect equilibrium. They're warmer than their surroundings. Energy still flows, however slowly, from them to the vacuum. But once they evaporate, once that last photon is emitted and redshifts into invisibility, the universe will settle into a state so close to perfect equilibrium that the distinction becomes academic. Except for one thing, quantum mechanics. Those zero-point fluctuations, the ones that prevent absolute zero from ever being reached, also prevent perfect equilibrium. Virtual particles continue to appear and disappear. Quantum fields continue to fluctuate. The vacuum maintains its irreducible energy density, its refusal to be perfectly still. These fluctuations don't care about temperature. They're not thermal. They depend on fundamental constants. Planck's constant, the speed of light, not on the temperature of their environment. So even at 10 to the power of minus 30, Kelvin, even at 10 to the power of minus 100, Kelvin, if we wait long enough, the quantum foam keeps bubbling, space keeps jittering, The vacuum keeps refusing to be empty. This is the universe's pulse, faint, nearly imperceptible but real. As long as quantum mechanics operates, as long as the uncertainty principle holds, the universe cannot achieve perfect stillness. There's something oddly comforting about this. In a cosmos that has grown so cold and empty that temperature has lost most of its meaning, where thermal motion has nearly ceased, where the stars are gone and the black holes are fading, quantum mechanics ensures that existence itself continues. Not life, not consciousness, not anything we would recognize as interesting or important, but existence being, the irreducible isness of reality. The universe at 10 to the power of minus 30. Kelvin is in a state we might call profound rest. Not sleep, because sleep implies the possibility of waking, and there's nothing to wake up to here. Not death, because death implies a prior state of life. Just rest. Deep, cold, patient rest. If the stelliferous era was the universe's youth, energetic, chaotic, full of change and transformation, and if the black hole era was its middle age, slower, more patient, but still dynamic, then the dark era is its old age. The universe has expended its energy. It has done its work. It has exhausted the gradients that make change possible. Now it rests. In meditation traditions, there's often an emphasis on achieving stillness, calming the mind, quieting the breath, settling into a state of deep peace. The goal isn't to stop thinking entirely, which is impossible as long as you're conscious, but to reduce mental activity to its minimum, to find rest within awareness itself. The dark era is cosmic meditation. The universe has settled into its ground state. Activity has reduced to the quantum minimum. Change occurs on timescales so long that calling them change seems generous. For all practical purposes, the universe has achieved stillness. But like a meditator who never quite stops thinking, the universe never quite stops fluctuating. Thoughts, virtual particles, arise and dissolve. The breath, expansion, continues its patient rhythm. Awareness, whatever that might mean in a cosmos without observers, persists in some abstract sense, encoded in the quantum states of fields that permeate all of space. The cold is profound, but it's not annihilation. It's presence at its minimum. Being without becoming, existence without event. And the temperature keeps falling. In another 10 to the power of 10 years, it will halve. And halve again, and again, forever approaching zero, never reaching it, asymptotically settling toward a limit that remains eternally out of reach. The universe grows colder, but it never freezes solid. It never stops entirely. Quantum mechanics won't allow it. In the profound cold of the dark era, in temperatures that make the depths of intergalactic space seem warm, in a stillness that approaches absolute, something persists. Not warmth exactly, not motion in any conventional sense, but the refusal of reality to become perfectly nothing. The universe is cold now, colder than cold, approaching the limit of coldness. But it never quite arrives. Everything solid you've ever touched, the ground beneath your feet, the chair you're sitting in, the walls of your room, your own body, is made of matter. Specifically, it's made of atoms. And atoms, as we learned in school, are made of even smaller things. Protons and neutrons clustered in a tiny nucleus, with electrons orbiting around them like planets around a star, except not really like that at all because quantum mechanics is strange. These building blocks seem permanent, fundamental, the bedrock of reality. Protons have been around since a few minutes after the Big Bang, when the universe cooled enough for quarks to bind together. They've persisted through 13.8 billion years of cosmic history without changing. Every proton in your body is roughly as old as the universe itself. They seem eternal. But seems is doing a lot of work in that sentence. According to the standard model of particle physics, our current best description of how particles and forces work, protons are perfectly stable. They don't decay, they last forever. Every experiment we've ever done confirms this. We've watched trillions upon trillions of protons for decades, waiting for just one to fall apart, and we've never seen it happen. But there's a catch. The standard model, as good as it is, isn't complete. We know this because it doesn't include gravity. It doesn't explain dark matter. It doesn't account for the apparent imbalance between matter and antimatter in the universe. These are hints that something deeper is going on, some more fundamental theory waiting to be discovered. Many of these deeper theories, collectively called Grand Unified Theories, or GUTS, predict that protons actually can decay. Not quickly, not on timescales we could easily measure, but given enough time, eventually a proton will spontaneously fall apart. The predicted half-life for a proton in most gut theories is around 10 to the power of 34 years. That's a 1 followed by 34 zeros. For comparison, the universe is currently about 10 to the power of 10 years old. A proton's half-life, if these theories are correct, is 10 trillion times longer than the current age of the universe. We're now in the dark era, at around 10 to the power of 70 years after the Big Bang. If protons decay with a half-life of 10 to the power of 34 years, then we've already passed through more than 10 to the power of 36 half-lives. The matter we knew is long gone. Here's how it would have happened. Slowly at first, then all at once, then slowly again, except the slowly and all at once are spread across timescales that make geological ages seem like eye blinks. In the first 10 to the power of 34 years, about half of all protons would have decayed. Not a specific half. You couldn't point to which proton survived and which didn't. It's random, probabilistic, quantum. Each proton has a 50-50 chance of making it through each half-life period. Some get lucky, most don't. When a proton decays, it doesn't just vanish. Energy is conserved, as always. The proton, made of 3 quarks bound together by the strong force, transforms into lighter particles. Usually a positron, the antimatter version of an electron, and a neutral pion. The pion immediately decays further into 2 photons, gamma rays. So a single proton becomes 1 positron and 2 photons. That's it. That's what happens to matter. It becomes light and antimatter. By 10 to the power of 35 years, 10 half-lives after the decay began, only about 0.1% of the original protons remain. The rest have transformed into radiation and positrons, spreading outward at the speed of light, red-shifting as the universe expands, cooling with a cosmic microwave background. By 10 to the power of 40 years, the decay is essentially complete. Whatever structures remained from earlier eras, white dwarfs, neutron stars, any stellar remnants that somehow survived the black hole era, have dissolved, not exploded, not collapsed, just quietly evaporated, 1 proton at a time, over trillions of years. Imagine a white dwarf, a stellar remnant about the size of Earth but with the mass of the Sun, made primarily of carbon and oxygen atoms packed into a crystalline structure. In our current era, white dwarfs are among the most stable objects in the universe. They don't burn, they don't collapse, they just sit there, slowly cooling, radiating away their residual heat over trillions of years. But in the proton decay era, that white dwarf is quietly dying. Each carbon atom contains 6 protons. Each oxygen atom has 8. The white dwarf contains something like 10 to the power of 57 protons in total, and one by one, randomly, these protons decay. At first, the decay rate is so low it's barely noticeable. 1 proton every few trillion years, then a few more. The white dwarf's mass decreases infinitesimally. Its structure remains intact. For now. But as time passes, the decay accelerates. Not because individual protons are decaying faster, but because we're moving through more half-lives. By 10 to the power of 35 years, the white dwarf has lost most of its mass. What remains is no longer solid, no longer bound by gravity into a compact sphere. It's a dissipating cloud of photons, electrons, and positrons, spreading outward into space. By 10 to the power of 40 years, the white dwarf is gone. Not even a cloud remains, just isolated particles, separated by light years, drifting through the expanding universe. Neutron stars face a similar fate, though the process is slightly different. A neutron star, as the name suggests, is made primarily of neutrons, particles that are slightly heavier than protons, and normally unstable. A free neutron, left to itself, will decay in about 15 minutes into a proton, an electron, and an antineutrino. But neutrons inside a neutron star are stabilized by degeneracy pressure, a quantum mechanical effect that prevents them from all decaying at once. They're packed so tightly that there's no room for decay products. The neutron star is held in a delicate balance between gravity trying to crush it further and quantum pressure pushing back. When proton decay begins affecting neutron stars, it destabilizes this balance. Protons in the neutron star decay into positrons and photons. The positrons can annihilate with electrons. The photons escape. Mass is lost. The degeneracy pressure weakens. And slowly, very slowly, the neutron star evaporates. It's a gentle process, spread across 10 to the power of 40 years. There's no explosion, no dramatic collapse, just a gradual unwinding, like a sandcastle dissolving in the tide, grain by grain, until nothing remains but beach. What's left after proton decay has run its course? Let's take inventory. Photons. Lots of photons. Every decayed proton produces at least 2, and there were about 10 to the power of 80 protons in the observable universe to begin with. So we've added about 10 to the power of 80 photons to the cosmic radiation background. These photons are massively redshifted by now, their wavelengths stretched by the universe's continued expansion, but they're there. Electrons, about 10 to the power of 80 of them, 1 for every proton that existed. Electrons, in most theories, don't decay. They're leptons, not baryons, and lepton number appears to be conserved even in gut theories, so the electrons persist. Positrons, also about 10 to the power of 80 of them, 1 for each proton decay. Positrons are antimatter, the antiparticle of electrons. When a positron and an electron meet, they annihilate, producing 2 photons. But in the dark era, with densities so low that particles are separated by vast distances, electrons and positrons rarely encounter each other. They can exist side by side in the universe, separated by light years, never meeting, never annihilating. They're like star-crossed lovers in a cosmic tragedy, destined to remain apart forever. Neutrinos. Enormous numbers of neutrinos produced in neutron decays and other processes. Neutrinos barely interact with anything. They can pass through light years of lead without noticing. In the dark era, with its vast emptiness, neutrinos are even more isolated than other particles. They drift through space, essentially free, carrying tiny amounts of energy, moving at very nearly the speed of light. And that's it. That's what matter becomes. The solid stuff of existence, atoms, molecules, rocks, planets, stars, everything, dissolves into radiation and leptons. The universe becomes a thin gas of light and nearly massless particles, all expanding away from each other, all cooling towards zero. There's something both melancholic and beautiful about this. Everything you can touch, everything solid and real, is temporary. Not just in the sense that your sandcastle will wash away or your house will eventually crumble, but temporary at the most fundamental level. Give it 10 to the power of 40 years, and atoms themselves dissolve. Buddhism teaches the concept of impermanence, that all conditioned things are transient, that nothing lasts forever, that clinging to permanence causes suffering because permanence is an illusion. Proton decay is the ultimate expression of impermanence. Even the seemingly eternal building blocks of matter are temporary, given enough time. But there's a caveat we should acknowledge. We don't actually know if protons decay. The experiments searching for proton decay have found nothing. The current lower limit on the proton half-life is about 10 to the power of 34 years, meaning that if protons do decay, they do so more slowly than this, but we haven't detected a single decay event despite watching vast numbers of protons for decades. It's possible that protons are truly stable, that the standard model is correct on this point, and that the grand unified theories predicting proton decay are wrong. In that case, matter persists. White dwarfs don't evaporate. They just cool, eventually becoming black dwarfs. Cold, dark, crystalline spheres drifting through space, completely inert, effectively eternal. But even if protons are stable, those white dwarfs and any other stellar remnants face another fate. They'll eventually encounter supermassive black holes or be ejected from their orbits and drift away. They'll spread out through the expanding universe, becoming isolated, unreachable. The matter persists, but it's effectively removed from the story, frozen, separated, incapable of interaction. Either way, whether through proton decay or through isolation, matter as a dynamic, interacting component of the universe is finished by the time we reach 10 to the power of 70 years. If protons decay, matter has dissolved into radiation. If protons are stable, matter has frozen into isolated, inert remnants that might as well not exist for all the influence they have on anything else. The dark era is fundamentally an era of radiation. Photons and leptons, light and nearly massless particles. The solid stuff is gone. This should feel profound, and it does, but it's worth remembering that even in our current era, matter is mostly empty space. An atom is a nucleus surrounded by electron clouds, but the nucleus occupies only about 1/trillionth of the atom's volume. The rest is emptiness, quantum fields in their ground state, potential rather than substance. So in a sense, matter has always been mostly illusion, mostly fields and forces with tiny knots of condensed energy we call particles. Proton decay just makes this explicit. It reveals what was always true. Solidity is temporary, substance is contingent, and the universe at its most fundamental level is made of fields and waves, not things. We're watching the universe shed its illusions, one proton at a time. And when the last proton decays, or when the last stellar remnant drifts beyond reach, what remains is closer to what the universe always was underneath: energy and space, fields and geometry, mathematics given barely physical form. The death of matter isn't tragic, it's honest. The universe is returning to itself. Imagine standing on the shore of an ocean so vast that the horizon curves away in every direction without interruption. No land breaks the view, no islands disturb the endless expanse of water. The surface is perfectly calm, no waves, no ripples, not even the subtle undulation of a distant swell. The water is so clear it seems almost absent, transparent all the way down to depths you cannot fathom. Now imagine that ocean continuing not just to the horizon, but beyond it, forever. And imagine the water molecules in that ocean are so far apart that you could sail for billions of years without encountering a single one. That's the Dark Era universe. An ocean of space so vast and so empty that calling it an ocean feels almost dishonest. But it's the best metaphor we have. In cosmology, we often treat the universe as a fluid, not because it's wet, it very much isn't, but because fluids are systems we know how to describe mathematically. A fluid has density, pressure, temperature. It can flow, expand, compress. And the universe, when you zoom out far enough that galaxies look like dust motes and clusters look like wisps of cloud, behaves remarkably like a fluid. In our current era, that cosmic fluid is clumpy. There are dense regions where matter has collected into galaxies and clusters. There are voids where almost nothing exists. The universe has structure, texture, variation. It's like an ocean with currents and eddies, warm spots and cold spots, regions of different density and composition. But in the Dark Era, all that structure is washed away. The expansion of space, driven by dark energy, has been smoothing out the universe for incomprehensible stretches of time. Any clumps of matter that once existed have either fallen into black holes or been scattered across distances so vast they might as well be in different universes. The radiation has been stretched and cooled until it's nearly uniform in every direction. Temperature is the same everywhere. Density is the same everywhere. The ocean has become perfectly still. Let's talk about what that ocean contains. Photons mostly, about 10 to the power of 88 of them, give or take a few orders of magnitude. These are photons from every source imaginable, ancient photons from the cosmic microwave background, now stretched to wavelengths measured in light years, photons from black hole evaporations, photons from proton decays if those occurred, all of them redshifted into near nothingness, barely distinguishable from the quantum vacuum. Electrons and positrons, if protons decayed, about 10 to the power of 80 of each, scattered throughout space, separated by vast distances, drifting slowly, very slowly through the expanding void. They rarely interact, rarely even come close to each other. Each one is essentially alone. Neutrinos, enormous numbers of neutrinos, perhaps 10 to the power of 80 or more, depending on various nuclear processes that occurred earlier in cosmic history. Neutrinos barely interact with anything, even in the dense, matter-rich universe of our era. In the Dark Era, they're ghosts among ghosts, passing through space, without touching anything, without being touched. Dark matter, if it's stable. We still don't know what dark matter is. Some new particle, probably, that doesn't interact electromagnetically and so remains invisible to telescopes. If dark matter particles are stable, they're still out there, making up a significant fraction of the universe's mass. But like everything else, they're spread impossibly thin beyond any meaningful interaction. And dark energy. Dark energy is the ocean's most dominant component, making up more than 99.9999% of the total energy density. It's everywhere, uniform, constant, unlike matter and radiation, which thin out as space expands. Dark energy maintains constant density. More space means more dark energy means faster expansion means more space, a feedback loop that has been running for 10 to the power of 70 years and will continue forever. The universe is fundamentally dark energy with trace impurities of particles and radiation. Let's get a sense of scale for how thin this ocean is. In your body, matter has a density of about 1 gram per cubic centimetre. That's fairly typical for biological tissue, close to the density of water. In the air you breathe, density drops to about 1,000th of that. In the best laboratory vacuums we can create, density is around 10 to the power of minus 17 grams per cubic centimetre. In the dark era, the average density of matter and radiation combined is something like 10 to the power of minus 120 grams per cubic centimetre. The best vacuum we've ever created in a laboratory would be crushingly dense compared to this. We're talking about a thinness that makes thin seem inadequate as a word. To give you a more visceral sense, if you could somehow grab a cubic metre of dark era space and examine its contents, you would find, on average, about one particle maybe. Depending on where you grabbed it and what counts as a particle for low-energy photons. And remember, the universe is expanding. The already impossibly thin density is getting thinner. Every 10 billion years or so, all distances double, which means volumes increase by a factor of 8. The same particles are now spread across 8 times as much space. Density drops by a factor of 8, and this happens again and again, forever. The ocean becomes thinner without limit, but it never becomes empty. Empty would mean 0 particles, 0 energy, 0 anything. The dark era universe always has something. Photons, leptons, dark energy, quantum fields. It's not a void, it's just extremely sparse. Presence stretched to its absolute minimum, while still counting as presence. Here's another way to think about the thinness. Imagine you're a photon, travelling at the speed of light through the dark era universe. You've been travelling for 1 billion years. In that time, you've crossed 1 billion light-years of space. How many other particles have you encountered? Probably none. The average distance between particles is measured in millions of light-years, possibly more. You could traverse the diameter of what used to be a galaxy cluster and encounter nothing, no gas to scatter off of, no electrons to interact with, no atoms to absorb or emit you, just empty space, or as close to empty as quantum mechanics allows. You are profoundly, cosmically alone. Now let's think about temperature and pressure, the other properties of our cosmic fluid. Temperature, as we discussed earlier, is approaching 10 to the power of minus 30 Kelvin. Effectively 0 for any practical purpose, though still technically above absolute zero because quantum mechanics. This temperature is uniform throughout space. No hot spots, no cold spots, no gradients. The ocean has reached thermal equilibrium. Pressure is even stranger. In normal fluids, pressure comes from particles colliding with each other and with container walls, creating a force that pushes outward. But in the dark era, particles are so far apart they never collide. There's no container, no walls. Classical pressure doesn't really apply. But there is still something like pressure, quantum mechanically. Dark energy has negative pressure. It pushes space apart rather than trying to compress it. This is why expansion accelerates rather than slowing down. The ocean isn't just still, it's actively trying to become larger, to stretch itself thinner, to increase its own emptiness. It's an ocean that wants to be less ocean-like. The homogeneity is remarkable. In the early universe, there were tiny density fluctuations, regions slightly denser than average, regions slightly less dense. These fluctuations, amplified by gravity over billions of years, created all the structure we see today: galaxies, clusters, superclusters, the cosmic web. But in the dark era, expansion has erased those fluctuations. Any region that was slightly denser has had its excess mass diluted across an ever larger volume. Any region that was slightly less dense has been stretched even thinner. The variation between different parts of space is now less than 1 part in 10 to the power of 50. For all practical purposes, the universe is perfectly smooth. If you could take a snapshot of a cubic million light-years of space here, and another cubic million light-years from somewhere 10 to the power of 30 light-years away, you wouldn't be able to tell them apart. Same density, same temperature, same composition, the universe has lost all its distinguishing features. This is both beautiful and eerie. Beautiful because there's an elegance to perfect symmetry, to a system that has settled completely into equilibrium. Eerie because it means the universe has no landmarks anymore, no way to distinguish one place from another, no narrative of change. In our ocean metaphor, it's as if every drop of water is identical to every other drop, and the ocean extends infinitely in all directions with no variation, no shores, no depths or shallows. You could drift for eternity and never know you've moved, because moving means nothing when all destinations are identical. Mathematically, the universe has become what cosmologists call a de Sitter space, a solution to Einstein's equations characterized by constant positive cosmological constant, dark energy, exponential expansion, and perfect spatial homogeneity. It's the simplest possible expanding universe, as featureless as geometry allows. There's something almost zen about this state. The universe has shed everything particular, everything individual, everything that makes one moment or place different from another. What remains is pure symmetry, pure simplicity, pure being without attributes. The ocean is no longer made of water molecules with their complex interactions. It's made of space itself, with dark energy providing the only substance, and particles appearing as the rarest of rare impurities in otherwise perfect emptiness. And yet, even in this profound stillness, motion continues. The expansion never stops. Every point in space is receding from every other point, driven by dark energy's negative pressure. Particles drift apart. The few photons that exist stretch to longer wavelengths. The cosmic event horizons shrink, isolating each region of space more completely from all others. The ocean flows in a sense, but it's a flow without currents, without direction, without purpose. Space expands homogeneously, meaning every part expands at the same rate. There's no place you could point to and say, the expansion is coming from there. It's everywhere and nowhere, all at once. If consciousness could exist in the dark era, and it almost certainly can't, what would it experience? Not loneliness, because loneliness requires the memory of companionship. Not boredom, because boredom requires the expectation of change. Probably just awareness of being, existence without content, presence without object. Perhaps that's what the universe itself experiences, if experience means anything when applied to a cosmos. Not thought, not feeling, not intention, just the bare fact of existing, of taking up space, of being present in the way that dark energy is present, everywhere, uniform, unchanging. The ocean simply is. There's a Taoist principle that water, despite seeming weak and yielding, is ultimately the strongest thing. It flows around obstacles. It adapts to any container. It wears away stone. Given enough time, water outlasts everything rigid and strong. The Dark Era universe has become like that Taoist water. It has yielded to entropy, adapted to expansion, worn away all structure, and now it persists, not through resistance, but through perfect adaptability. It has no form to lose, no structure to break, no complexity to unwind. It has already unwound completely. This is the lowest energy state possible for a universe with dark energy. Not a true vacuum, quantum fields still fluctuate, but the closest thing to equilibrium that physics allows. The ocean has settled into its most natural shape, which happens to be featureless, boundless, and nearly empty. And it will remain this way forever, or something very close to forever. Longer than the universe has currently existed, longer than the ratio between the age of the universe and the lifetime of a photon crossing a proton longer than numbers can usefully express. The ocean is patient. It has nothing but time. We've been swimming in metaphors, but let's surface for a moment and acknowledge what we're actually describing. A universe that has reached maximum entropy, or very nearly so. Entropy is a measure of disorder, but more precisely, it's a count of how many different microscopic states correspond to the same macroscopic state. A high entropy system is one where many different arrangements of particles produce the same observable properties. The dark era universe has enormous entropy because almost any arrangement of its particles would look the same, perfectly smooth, perfectly uniform, perfectly boring. This is the heat death state that thermodynamics has been threatening since the 19th century. Not death in the sense of cessation, but death in the sense of perfect equilibrium, where no further change is possible because no gradients exist to drive it. The ocean has stopped flowing because there's nowhere for it to flow to. Every point is equivalent to every other point. Every moment is equivalent to every other moment. The universe has achieved a kind of timeless, spaceless existence, not because time and space have ended, but because nothing happens to mark time's passage or space's extent. And yet, the ocean is still there, still real, still taking up infinite space, still existing in each moment. Silent, yes, empty, mostly. Still, profoundly. But not gone, never gone. Just resting in its most natural state, the way water rests at the bottom of a valley, having finally reached the lowest point gravity allows. Stillness, we've learned, is impossible. The universe cannot rest perfectly. It cannot achieve absolute zero. It cannot find complete equilibrium. Not because it hasn't had enough time, it's had essentially infinite time, but because the laws of physics simply won't allow it. This is Heisenberg's uncertainty principle at work, that fundamental feature of quantum mechanics that says certain pairs of properties cannot both be precisely defined position and momentum, energy and time. The more precisely you know one, the less precisely you can know the other. This isn't a measurement limitation or a technological constraint. It's built into the fabric of reality. One consequence of this uncertainty is that energy can briefly violate conservation, but only briefly, and only by an amount inversely proportional to the duration of the violation. Borrow a lot of energy, and you must pay it back almost instantly. Borrow a little, and you have slightly longer. This leads to one of the strangest features of quantum mechanics. The vacuum isn't empty. Even in a region of space containing no particles, no radiation, no fields in excited states, what we'd classically call nothing, quantum fields are still there, still fluctuating, still producing what physicists call virtual particles. These are particle-antiparticle pairs that pop into existence, exist for a tiny fraction of a second, then annihilate each other and disappear. They're called virtual because they don't last long enough to be directly observed, but they're real in the sense that they have measurable effects. The Casimir effect, for instance, where two metal plates in a vacuum are pushed together by the pressure of virtual photons, is direct experimental evidence that these fluctuations exist and carry real energy. In the dark era, with its profound cold and near-perfect stillness, these quantum fluctuations become the dominant form of activity. They're not the only thing happening. The expansion continues, particles drift apart, but they're the only interesting thing happening. Everything else is just patient geometry and slow separation. Virtual particles appear and disappear throughout space, constantly, everywhere. The rate at which this happens doesn't depend on temperature or the age of the universe. It depends only on fundamental constants, Planck's constant, the speed of light, the masses of particles. These don't change with cosmic epoch. So in the dark era, virtual particles appear at the same rate they always have. An electron-positron pair fluctuates into existence, exists for about 10 to the power of minus 21 seconds, then disappears. A pair of photons appears and vanishes. Heavier particles, quarks, W and Z bosons, even virtual Higgs particles, flicker in and out of existence on timescales measured in 10 to the power of minus 24 seconds or less. This is happening everywhere, all the time. In every cubic meter of space, virtual particles are appearing and disappearing at a rate of roughly 10 to the power of 50 pairs per second, depending on which particles you're counting and what energy scale you're considering. That sounds like a lot, and it is a lot. But remember, space is vast. The observable universe, or what was once observable, contains something like 10 to the power of 80 cubic meters. Multiply that by 10 to the power of 50 fluctuations per cubic meter per second, and you get 10 to the power of 130 virtual particle pairs, appearing and disappearing every second throughout the universe. It's an enormous number, but these particles aren't doing anything. They're not interacting with anything. They appear, exist briefly in a quantum superposition of states, then annihilate. They're like thoughts that arise in meditation, present, real in their moment, but gone before they can develop into anything substantial. The vacuum is thinking itself into existence and then forgetting itself over and over forever. Now here's where things get interesting, or as interesting as things can get in an era defined by nothing happening. Usually virtual particles appear in pairs and annihilate so quickly that they return their borrowed energy before the universe notices. But occasionally, very occasionally, something else happens. The pair separates before they can annihilate. One particle escapes, becomes real, and the energy debt is paid by some other source. Near a black hole, this is how Hawking radiation works. A virtual pair appears at the event horizon. One particle falls in, the other escapes. The black hole loses mass energy equal to the escaping particle. From outside, it looks like the black hole is radiating. But in the dark era, there are no black holes nearby, at least none close enough to matter. So where does the energy come from if a virtual particle becomes real? From dark energy, possibly, or from quantum tunneling, a process where the universe momentarily violates energy conservation by tunneling through an energy barrier, with the probability of this happening determined by quantum mechanics. The probability is extraordinarily low. For an electron to spontaneously appear from the vacuum without a corresponding positron nearby to annihilate with, the probability is something like 10 to the power of minus 1 million per cubic meter per second. That's a decimal point followed by a million zeros, then a 1. Absurdly unlikely, but we have absurd amounts of time and space to work with. Over 10 to the power of 100 years, a time frame we'll reach eventually if we wait long enough. Even events with probabilities of 10 to the power of minus 1 million become not just possible but likely, not in any particular place, but somewhere in the vast expanse of space. It will happen. An electron appears, not from a proton decay, not from a particle collision, just appears, borrowed from the quantum vacuum, and if it appears far enough from other particles, it might never find its antiparticle to annihilate with. It becomes a permanent addition to the universe. This is happening incredibly rarely, but rare times infinite duration equals eventually common. Now let's talk about something even stranger, Boltzmann brains. Ludwig Boltzmann was a 19th century physicist who helped develop statistical mechanics and our understanding of entropy. He realized that if you wait long enough, random thermal fluctuations could spontaneously create any configuration of particles, no matter how complex or unlikely. Given infinite time, fluctuations could create a teacup, or a book, or a human brain, complete with memories and thoughts, which exist for a single moment before dissipating back into randomness. These hypothetical spontaneous brains are called Boltzmann brains, and they're considered a problem for cosmology. If the universe exists in a heat-death state for infinite time, and random fluctuations can create observers, then most observers in the universe's history would be Boltzmann brains, spontaneous, short-lived, with false memories, rather than evolved biological beings like us. This seems absurd, and most physicists think it's probably wrong, that there's something about our understanding of cosmology or quantum mechanics that prevents Boltzmann brains from dominating. But we can't entirely rule them out. In the dark era, thermal fluctuations are negligible. The temperature is too low, but quantum fluctuations continue, and quantum mechanics allows for tunneling events that could, in principle, create complex structures. The probability of a quantum fluctuation creating something as complex as a brain is roughly 10 to the power of minus 10 to the power of 50. That's not a typo. It's 10 to the power of negative 10 to the power of 50, a probability so small that the exponent itself requires an exponent. But infinity is patient. Over timescales of 10 to the power of 10 to the power of 100 years, which will eventually arrive if the universe continues as it has, even this becomes possible. Somewhere, at some incomprehensible time in the future, a brain might spontaneously appear from quantum fluctuations. It would think for a fraction of a second, probably not coherent thoughts, more like random neural firings, and then dissolve back into particles. Its existence would be meaningless, its experience nonsensical, its appearance and disappearance without consequence. But it would happen. Probably. Maybe. We don't actually know. This is the kind of territory we're in now. Not just science, but philosophy and speculation. We've gone so far beyond the realm of testable predictions that we're working with pure mathematical extrapolation. The equations allow it, but the equations might be wrong. The universe might not last this long. Vacuum decay might reset everything. Some unknown physics might intervene. But if none of that happens, if the universe simply continues being what it is now for arbitrarily long periods, then quantum mechanics says, given enough time, anything possible will happen, not just once, but infinitely many times. Let's come back to something more grounded, the quantum fields themselves. The universe isn't made of particles, really. It's made of fields, the electron field, the quark fields, the electromagnetic field, the Higgs field. Particles are just excitations of these fields, like ripples on a pond. An electron is a localized excitation of the electron field. A photon is a ripple in the electromagnetic field. When we say the vacuum is empty, we mean all these fields are in their ground state, no excitations, no particles. But the ground state isn't zero energy. It's the lowest energy the field can have while still respecting quantum mechanics. Each field contributes what's called zero-point energy to the vacuum. Add up the zero-point energy of all fields, and you get the vacuum energy density. This should be related to dark energy, the cosmological constant, but when we do the calculation, we get a number that's about 10 to the power of 120 times too large. This is called the cosmological constant problem, and it's one of the biggest unsolved problems in physics. Why is the vacuum energy so much smaller than quantum field theory predicts? We don't know. Various explanations have been proposed: supersymmetry, string theory, anthropic reasoning, but none are entirely satisfying. The dark era doesn't solve this problem. It just makes the question more acute, because in a universe dominated entirely by vacuum energy, understanding what vacuum energy actually is becomes kind of important. But whatever vacuum energy is, it's there in the dark era, making up essentially 100% of the universe's energy density. Matter and radiation have become negligible. Dark energy is everything, and dark energy comes with quantum fluctuations. The cosmological constant isn't perfectly constant at the quantum level. It fluctuates slightly, randomly, creating tiny temporary variations in the expansion rate. These fluctuations are incredibly small, far too small to measure. But they're there, a reminder that even the smoothest, most uniform things still have quantum texture. The vacuum breathes, in a sense, not rhythmically, not purposefully, but restlessly. It cannot achieve perfect stillness because quantum mechanics forbids it. There's something almost comforting about this. In a universe that has grown so cold and empty that nothing interesting can happen anymore, quantum mechanics ensures that existence continues, not life, not consciousness, not anything we'd recognize as meaningful, but existence, activity at the absolute minimum level physics allows. The universe has a pulse, faint, rapid, meaningless, but real. In meditation practices, there's often discussion of the subtle body, the barely perceptible sensations that remain when gross physical sensations have quieted. The breath becomes so soft it's almost undetectable. The heartbeat fades from awareness. But if you pay very close attention, you can still feel something. Tiny vibrations, energy flows, the irreducible aliveness of being embodied. The quantum fluctuations in the dark era are like that subtle body. The universe has quieted all its gross processes: star formation, galaxy collisions, black hole evaporation. What remains is the subtle level, the quantum breathing, the vibration that cannot be stilled. And this will continue forever. Not because quantum mechanics might change, as far as we know it's fundamental, but because forever is built into the dark era's structure. The universe isn't building toward anything, isn't waiting for anything, isn't evolving toward any particular state. It's just existing, moment by moment, with quantum fluctuations providing the only variation in an otherwise perfectly uniform existence. The vacuum flickers, and that flickering is the universe's answer to the question, can nothing happen? No, nothing cannot happen. Even in the most extreme conditions, even in near-perfect stillness, even at temperatures approaching absolute zero across distances approaching infinity, something happens. Virtual particles appear and disappear. Fields fluctuate. Uncertainty refuses to resolve into certainty. Being refuses to become nothingness. The universe insists on existing, even when existence has been stripped down to its barest possible form. And that insistence, that irreducible presence, that refusal to be perfectly still is perhaps the most fundamental thing about reality. Not matter, not energy, not space or time, but the simple fact that quantum mechanics won't let anything be perfectly nothing. The flickers continue. They've continued for 10 to the power of 70 years. They'll continue for 10 to the power of 1,000 years, for 10 to the power of 10 to the power of 100 years, for timescales that make forever seem like a conservative estimate. The universe is patient, the vacuum is restless, and together they persist in this strange dance. Perfect stillness interrupted by imperceptible motion, complete equilibrium undermined by quantum uncertainty, absolute silence containing the faintest possible whisper. The flicker is all that remains, but the flicker is enough. Silence can feel oppressive. The awkward pause in conversation, the empty house after everyone has left, the stopped clock that used to tick. We're wired to interpret silence as absence, as something missing, as a void that should be filled. But silence can also be presence, the focused quiet of deep concentration, the stillness of fresh snowfall, the peace after a storm has passed. In these moments, silence isn't the absence of sound. It's a quality of experience, a state of being, something positive rather than merely negative. The dark era's silence is both. It's the silence of ending. The last note has faded, the players have left, the stage is empty. But it's also the silence of being, the universe at rest, having completed its work, settled into equilibrium, found peace. Let's talk about what this silence means, and whether meaning is even the right word to use. The universe has reached a state that physicists call heat death, though the name is misleading. Nothing has died exactly. The universe still exists. Space still expands. Quantum fields still fluctuate. Particles still drift through the void. But what has ended is the possibility of change, or more precisely, the possibility of organized, directional change that we might call events or processes or narratives. Heat death doesn't mean everything is hot. It means everything is the same temperature. And when everything is the same temperature, heat cannot flow. Energy cannot move from hot to cold because there is no hot and cold, only uniform warmth, or in this case, uniform coldness. The second law of thermodynamics says that entropy always increases in a closed system. Entropy is often described as disorder, but more precisely, it's a measure of how many microscopic arrangements of particles correspond to the same macroscopic state. High entropy means many possible arrangements all look the same from the outside. The dark era universe has enormous entropy. Almost any arrangement of its particles would produce the same observable properties: uniform temperature, uniform density, no structure, no variation. The universe has explored essentially all of its available states and found them all equivalent. This is maximum entropy, or close enough that the distinction doesn't matter. And at maximum entropy, nothing further can happen. Not because time has stopped, but because there are no gradients left to drive processes, no potential differences to create flows, no asymmetries to break symmetry. The universe has run out of interesting things to do. But here's the question that makes this more than just a physics discussion. Does this matter? The universe doesn't care, presumably. It has no preferences, no goals, no sense of loss or accomplishment. It simply is what it is. A vast expanse of nearly empty space, expanding forever, approaching but never reaching perfect equilibrium. But we care, or at least we might care, because we're here now, in the brief energetic phase before heat death, and this is our context. The dark era tells us something about the nature of our own existence. Specifically, we are extraordinarily rare. If you were to pick a random moment in the universe's history, weighting each moment equally, you would almost certainly pick a moment in the dark era. The stelliferous era, when stars form and burn, lasts about 100 trillion years. The black hole era extends that to perhaps 10 to the power of 100 years if we're generous. But the dark era lasts forever, or close enough that infinity seems like a reasonable approximation. The ratio of universe with interesting stuff happening to universe in heat death is roughly 0. We exist in a tiny, improbable sliver of cosmic time when energy gradients still exist, when stars still burn, when complexity is still possible. This isn't an accident. Complex structures like stars and planets and life require disequilibrium. They need energy flowing from hot sources to cold sinks, creating opportunities for organization and pattern. Heat death precludes all of this. Not because it destroys complexity, the universe doesn't actively destroy anything, but because it erases the conditions that allow complexity to form or persist. This leads to what's called the anthropic principle. We observe the universe during this particular era, because this is the only era during which observers can exist. If you need stars to create heavy elements, and planets to provide stable environments, and energy gradients to power metabolism, then you necessarily find yourself existing during the brief window when these things are available. The dark era has no observers, because observation requires complexity, requires disequilibrium, requires an era that isn't heat death. So from a certain perspective, the dark era doesn't matter, because there's no one there for it to matter to. It's a universe without witnesses, a story without readers, existence without experience. But from another perspective, the dark era matters enormously, because it provides context for everything that came before. Without silence, sound has no meaning. Without darkness, light means nothing. Without the heat death that will eventually claim everything, the stelliferous era's temporary brightness becomes precious exactly because it's temporary. Cherry blossoms are beautiful because they fade. Love is meaningful because it's finite. Consciousness is extraordinary because it's rare. The universe's energetic phase is valuable, if value means anything in a cosmic context, precisely because it doesn't last. The dark era is the frame that makes the picture make sense. There's a Buddhist concept called anicca, impermanence. All conditioned things are impermanent. Everything that arises will eventually cease. This isn't meant to be depressing. It's meant to be liberating. If nothing lasts forever, then nothing, including suffering, lasts forever. The heat death of the universe is the ultimate expression of anicca. Not just individual things fade, but the very possibility of things arising stars form and die, galaxies merge and disperse, and eventually the conditions that allow for formation and dissolution themselves dissolve. Everything returns to equilibrium, everything settles, everything rests. And there's peace in that, perhaps, not the peace of relief or comfort. The universe doesn't experience relief, but the peace of completion. The universe has done what thermodynamics required it to do. It has increased entropy to its maximum. It has explored its state space. It has become what it was always going to become. Purpose fulfilled, if purpose is the right word. Now let's think about time. We experience time as change. Memory works by recording changes in brain states. Causality is the relationship between earlier changes and later changes. Clocks measure change. The swing of a pendulum, the oscillation of a quartz crystal, the decay of radioactive atoms. In the dark era, meaningful change has essentially stopped. Quantum fluctuations continue, but they're random, uncorrelated, leading nowhere. The expansion continues, but it's just geometric scaling, all distances growing proportionally, which means the universe at time t looks identical to the universe at time 2t, except everything is bigger. Does time still exist when nothing changes? Physics says yes. The parameter t continues to advance in the equations. Space-time still has a time dimension. The universe doesn't freeze at some final moment. It keeps going, moment after moment after moment. But experientially, if there were anyone to experience it, time would become strange. How do you measure duration when there are no events to count? How do you distinguish one moment from the next when each moment is identical? It would be like trying to tell time in a room with no clocks, no windows, no changes in light or sound. Time is still passing. Your cells are still metabolizing, your neurons still firing, but without external markers, you'd lose track. Minutes and hours would blur together. In the dark era, there are no external markers, no processes that take predictable amounts of time, no cycles to track, just the smooth, featureless flow of moments that differ from each other only in their timestamp. Time becomes abstract. It exists mathematically but has no texture, no structure, no meaningful divisions. And yet it continues, forever, or as close to forever as makes no difference. There's something almost meditative about this vision of time, duration without content, flow without change, existence without events. In certain contemplative traditions, this is described as a goal, to experience pure awareness without objects of awareness, to exist in the present moment without past or future, to find stillness beneath the surface turbulence of thought and sensation. The dark era achieves this by default. It has no choice. It's pure duration, pure existence, pure being. Whether that constitutes some kind of cosmic enlightenment or just the inevitable consequence of thermodynamics is probably a matter of interpretation. Let's talk about meaning itself. In information theory, meaning can be defined as organized complexity, patterns that carry information, structures that deviate from randomness in systematic ways. A book has meaning because its letters are arranged non-randomly to form words and sentences. White noise has no meaning because it's purely random. By this definition, the heat-death universe has essentially no meaning. It's maximally random. Any measurement you make is uncorrelated with any other measurement. There's no information to extract because there are no patterns, no structures, no organization above the absolute minimum quantum mechanics requires. But perhaps that's too narrow a definition. Perhaps meaning doesn't require complexity or information. Perhaps existence itself has meaning, the sheer fact of being, regardless of organization or pattern. The dark era exists. Space exists. Time exists. Quantum fields exist. That might be enough. Or perhaps meaning is something we project onto things rather than something inherent in them. We find meaning in sunsets and symphonies and scientific discoveries because we are conscious beings with values and preferences and the ability to care about things. The universe itself doesn't find meaning in anything because it doesn't find. It just is. In that case, the dark era is neither meaningful nor meaningless. It simply exists beyond the category of meaning, like asking what color a sound is or what temperature virtue has. The question doesn't quite apply. But for us, here now, in the brief moment before heat death claims everything, the dark era can be meaningful as context, as ending, as the final state that gives shape to all the temporary states that preceded it. It tells us this is where everything is going. Complexity is temporary. Structure is ephemeral. The default state of the universe is nearly empty, nearly uniform, nearly unchanging. Everything else, stars, planets, galaxies, life, consciousness, the entire rich texture of existence, is a brief deviation from equilibrium, made possible by the universe starting out in a very low entropy state and taking a long time to reach maximum entropy. We are the universe in its youth, its energetic phase, its moment of maximum possibility. The dark era is the universe in its final state, its rest, its completion. And there's something beautiful about having both, the beginning and the ending, the complexity and the simplicity, the sound and the silence. One gives meaning to the other. If the universe ended in a big crunch, all matter collapsing back to a singularity in a mirror of the Big Bang, that would be dramatic, but somehow less final. It would feel like a story with a definite ending, perhaps even a cyclical story that repeats. Heat-death is different. It's not an ending in the narrative sense. It's an asymptotic approach to a limit. The universe keeps going, but it stops changing. It reaches a state, and stays there, not for a fixed duration, but forever. This is both more honest and more unsettling than a definite ending. The universe doesn't conclude, it doesn't roll credits and fade to black. It just continues, existing, being, persisting in its heat-death state without possibility of escape or transformation. Unless something we don't know about intervenes. Vacuum decay, perhaps, which we'll explore next, or some exotic quantum process that operates on timescales so long we can't even imagine them, or physics we haven't discovered yet. But based on what we currently understand, heat death is final, not in the sense of cessation, but in the sense of completion. The universe reaches its maximum entropy state and stays there. The silence becomes permanent. And yet, even in that permanent silence, something persists. The quantum fluctuations we discussed earlier, the expansion of space, the existence of fields and geometry and time itself. The universe doesn't become nothing, it becomes quiet. Very, very quiet. But not nothing, never nothing. There's a Zen koan. What is the sound of one hand clapping? It's meant to point beyond dualistic thinking, beyond the idea that sounds require pairs of objects striking each other. One hand can't clap in the conventional sense, but the question asks you to find the sound anyway. The dark era is the sound of one hand clapping, its existence without events, duration without change, presence without objects. It shouldn't be able to sound because there's nothing happening to make sound. And yet something is there. The universe persists. Time continues. Space expands. The silence has a quality, a texture, a presence. And in its own strange way, that presence is the purest form of existence, being stripped of all attributes except being itself. The universe in the dark era isn't doing anything. It isn't becoming anything. It just is. And perhaps that's not a tragedy. Perhaps it's an achievement. The universe has found rest. It has exhausted its possibilities and settled into its ground state. It has become what it was always going to become, given infinite time and the second law of thermodynamics. Purpose fulfilled, work completed, change ended. Now only the eternal present remains, each moment identical to every other moment, stretching forward without limit, without destination, without meaning, except the meaning we might give it from our brief vantage point in the universe's energetic youth. The silence is complete. The silence is profound. The silence is permanent. And the silence, in its way, is perfect. We've travelled through the dark era together, the universe's longest chapter, an epoch of silence and stillness that will outlast all previous eras by factors too large to comfortably express. We've watched temperatures approach absolute zero, witnessed distances grow beyond comprehension, seen matter possibly dissolve into radiation, and observed the cosmos settle into something approaching perfect equilibrium. We've learned that the dark era is characterized not by drama but by profound rest. No explosions, no collisions, no sudden transformations, just the patient expansion of space, the gentle cooling towards zero, quantum fluctuations providing the only variation in an otherwise uniform existence, the universe at peace, having exhausted its available energy, completed its transformations, found its ground state. And there's a kind of beauty in that vision, not despite its emptiness, but because of it. The universe needs no audience. It requires no meaning. It simply is, and that sufficiency is remarkable in its own way. But here's the thing. We've been assuming the dark era is final. We've been treating heat death as the end of the story, Not an ending with closure, but an asymptotic approach to a state the universe will maintain forever. Maximum entropy, perfect equilibrium, eternal stillness. And that might be true. Based on our current understanding of physics, the heat-death state appears stable, irreversible, permanent. But current understanding is doing a lot of work in that sentence. Physics has surprised us before. Quantum mechanics revealed that particles can tunnel through barriers they shouldn't be able to cross. General relativity showed us that space and time are dynamic, that the universe had a beginning, that black holes can evaporate. Dark energy taught us that the universe's expansion is accelerating, not slowing down as we expected. Each of these discoveries fundamentally changed how we think about the cosmos. Each revealed that what seemed permanent was actually temporary, that what seemed impossible was actually inevitable, that what seemed settled was actually just beginning. And there are hints, theoretical hints, mathematical possibilities, speculative but rigorous ideas, that the dark era might not be final after all. Vacuum decay could reset the universe, transforming it into something with entirely different physics. Quantum tunneling might create new universes from the quantum foam. The multiverse might be real, with our heat-death just one bubble in an infinite effervescence of cosmic creation. Time itself might be cyclic, with heat-death serving as a transition rather than an ending. These aren't wild fantasies. They're serious proposals from theoretical physicists, grounded in mathematics and extrapolations of known physics into regimes we can't yet test. They might be wrong. Many theoretical ideas turn out to be wrong when confronted with better data or deeper understanding. But they might be right. And if any of them are right, then everything we've said about the dark era being permanent needs qualification. It might not be the end. It might be a pause, an intermission, the longest possible silence before something new begins. That's what we'll explore in our next journey together. Episode 3. What comes after the universe ends? We'll venture into the speculative territory where established physics meets cutting-edge theory, where mathematics suggests possibilities that seem impossible, where the question, what happens after forever, gets taken seriously. We'll investigate vacuum decay and false vacuum states, quantum tunneling and baby universes, eternal inflation and the multiverse, cyclic cosmology, and the possibility that time itself might restart. We'll ask whether consciousness could persist, whether information survives, whether anything from our universe could carry forward into whatever comes next. It will be more speculative than what we've covered so far, less certain, more dependent on theories that haven't been tested and might never be testable. But it will be rigorous, grounded in actual physics and mathematics, exploring genuine possibilities rather than mere fantasies. If you'd like to continue beyond the dark era's silence, to ask whether silence might eventually break, whether endings might contain beginnings, whether the universe's story has chapters we haven't imagined yet, join me for that next exploration. For now, though, let's rest here in the quiet we've found. The dark era is real, whether or not it's permanent. The universe will spend incomprehensible amounts of time in this state, and there's value in understanding it, in sitting with it, in contemplating what it means for existence to continue in the absence of change. Thank you for journeying with me through this vast silence. If it brought you peace, helped you sleep, or gave you a new perspective on time and existence and the nature of endings, then I've succeeded. The universe rests in profound stillness. Quantum fields fluctuate gently. Time passes without events to mark it. And somewhere beyond the silence, perhaps, a question waits. Is this truly the end? Or is it just the longest pause before something we can't yet imagine? This is the Sleepy Astronomer, wishing you good night. Sleep well. The silence is patient. The darkness is deep. And the question remains,